So we could put B to the end of the list. The question is, how would you do that? Well, if B was here previously, what we could do is start at node A. Let's say there are a bunch of nodes between A and B. Keep iterating the pointer, like A.next and A.next.next. Keep creating a new pointer. We're updating the value of the pointer all the way until we get the value B. So every time we get a new value, we check if it equals B. If it does equal B, we then we keep a reference to the node before B, and then we get that previous node. We set previous.next equal to C, and then we also take B over and set D.next equal to B. So we have to essentially do a bunch of pointer logic, and we got to iterate through the whole list. That takes O(n) of time, where n is the number of nodes in the list. Using a different structure called a doubly linked list, we can essentially remove and add. We can remove items from the list in constant time. For example, if A was linked to B and B was linked to A in both directions, using like a previous and a next dot node, previous and next pointers. All you really need to do to, let's say, push B to the end is we can say D.next equals B. We can say B.previous equals D. So essentially, D.next equals B and B.previous equals D. And then we can also, so we just changed B.previous, so B no longer points to A. And then we also say A.next is equal to C. And we say C.previous points to A. So that is like 4 operations. We just moved a node. Instead of n operations, it's 4 operations. It's constant time. So we're going to create something called a doubly linked list. We're just going to have something called doubly linked node. And that will let us solve the problem. So to make our... Okay, so if you look at this list right here, weird, hard logic can occur. So let's say you want to move A in front of B. Well, you could say A.next equals B, you could say B.previous equals A. But using our previous example before, we were moving B to the end of D. Here we would have said B.previous .next is equal to C. We're kind of disintegrating B right there. That's fine right here, because B.previous equals A. Let's say we're removing A right here. A.previous equal to null. So in that kind of logic, whatever method we were writing right there, we would have had to say, if A.previous does not equal null, then A.previous.next is equal to A.next. So we have to add some if statements, kind of makes our code messy. So what we're actually going to do is add some dummy nodes to our doubly linked list. So we're going to have a node called head, which is kind of like the front of the list, and then we're going to have our data, our real data nodes, and then we're going to have our tail. And that's might get rid of some of our if statements. I guess we'll see. I don't quite remember. So we're going to add a constructor. And essentially, I'm going to say this dot head is equal to new DL node. This dot tail is equal to new DL node. And by default, we're just going to connect head and tail to each other such that our list looks like this. So this dot head dot next equal this dot tail. This dot head dot previous, always going to be null. This dot tail dot next be null. This dot tail dot previous is going to be equal to this dot head. And then we're going to have our constructor for our DL node class. And we're essentially going to say, you know, this dot key equals key, this dot value equals value. The reason we're having key value pairs is just to store, I don't know, the kind of domain specific. We're using key and value in our data structures. Our node is not supposed to store the key or the value. Do we want the key and the value? Maybe we don't need one of them. I'm not sure. I have to think about that more. So we can say this dot. So a doubly linked node is going to have next and previous properties. We kind of implicitly said that they do here, and we're going to publicly expose those, let other classes modify them. Not necessarily good design, but it works here. So this dot previous is going to be null. This dot next equals null. Okay, so now we have these data structures. Let's use them. So we're going to say, oh, our list is also going to have a size. So, thinking through use cases here, we essentially, whenever we add a new item to your cache, we want to add it on to, I guess, the tail of our list. And whenever we want to remove an item, we just want to remove that item such that we can put it on the end of the list. And yeah, that's really what we want. So we need add and remove methods on list. So let's have a remove method. So it's actually pretty straightforward. We okay, so we're just gonna assume that node is never equal to head or tail. And we'll show how we can prove that loop invariant holds, that precondition holds rather. Show above precondition is always satisfied. And yeah, so we'll get into that. But for now, we just say node dot previous. Well, let's just kind of draw right here. So we're essentially saying that so okay, let's remove C from the list. So previous dot next must equal C dot next, and next dot previous must equal C dot previous. So node dot previous dot next must equal node dot next, and node.next.previous must equal node.previous. And now that we have changed where the previous and next point to, we can also make, yeah, so essentially, so now we can also remove what C pointed to. This pointer logic, I'd recommend drawing out on pencil and paper, kind of hard to think about in your head. I've already done it though, so I can think of it in my head. So we're gonna make it so that the node now can't reach. Okay, so this prevents any other items in the list from being able to reach node, and this can prevent node from being able to reach its siblings in the list as well. All right, and then we're gonna have an append method. We're never gonna add an item just anywhere in the list. We're gonna add it only at the end. So this is also an easy method as well. We're gonna say this. 1 second. We're gonna say this dot. We're gonna say, so this is why we have these dummy nodes right here. It kind of makes. Actually, this isn't why we have the dummy nodes. We explained why we don't have the dummy nodes. I mean, why we do have the dummy nodes. Rather than like saying this dot tail dot append, remember our last data item is actually going to be right before tail. So we're gonna say this dot tail dot previous dot next is equal to node. It's a lot of indirection here. I guess a better way to do it would be current last data node is equal to this dot tail dot previous, because tail is like beyond the last data node. Tail dot previous is the last data node. So we're gonna say current last data node dot next is equal to node, and I'm going to say node.previous is equal to this, current last data node, and then I'm going to connect node to tail. So I'm going to say this dot tail dot previous equal node, and node dot next is equal to this dot tail. So when we are putting an item, we need to add it to our list. So we can say this dot list dot append we also need to track the size of our lists. So I'm going to say this dot size minus minus on remove, and I'm going to say this dot size plus plus on append. So there we go. We're adding our node. The thing, however, is if we were at capacity before adding this node, we need to remove a node beforehand. So okay, we're going to change some things around here, and it'll make sense in a few minutes. We're not going to store the value of the key value pair in the map. We're going to store the node in the linked list. So first thing we're doing when we're checking a put is if the node, the linked list node for that key value pair exists yet. So we're going to say const node, check if the node exists, equals this dot map key. And if node exists, then we know that we aren't adding a new node, rather we're just kind of updating the value if the key exists, following this instruction right here. So if the value already exists, what we need to do is essentially, let's say we're just updating the value of C right here, we need to remove C from the list and then add it on to the end of the list. So so we already know that the node exists in our hash map, so we're just literally going to call this dot list dot remove node, and then this dot list dot append node, removing from the list and then adding it back in at the right position. If node doesn't exist, we need to add it to the cache as a new node, and check if the whole capacity thing is correct. So else, we're adding a new node. We need to check if we're already at capacity. So if list.list.size is equal to this dot capacity, we want to remove the least recently used node. Well, what's the least recently used node? It's going to be the one at the front of the list, because we add to the end, we add to the last, and things get pushed to the front. So essentially, when you use an item, it keeps getting refreshed, recycled back to the end of the list and end of the line. And when you don't use something, it gets able to progress to the front of the line. So things at the front of the line are going to be those that were least recently used. So we want to this dot list dot remove the front item. So let's make a method for that. Let's make, remove front. And essentially, we're just going to get the front node, and we're just going to assume, again, we're going to assume, this dot head dot next is not equal to tail. Just going to assume it gets called correctly. So const front is going to equal this dot head dot next. We might have to return that. We'll figure that out later. And we're going to call this dot remove front. Yep, here we go. And what we also need to do is we just deleted the front node from the list. We also need to delete it from the hash map because when well, first let's update the get method of the hash map and you'll see what I'm getting at. So remember, now in the hash map we're storing node, or in the dictionary we're storing node. If node exists, if node does not exist, you turn -1. If it does exist, we're going to turn node.value, because val is a property on the DL node. Yep. So anyway, when we remove an item from the list, we also need to remove it from the dictionary, because otherwise get wouldn't return -1, because it would still be in there, even though it no longer belongs to the list. The node still exists in the JavaScript memory heap. It's still going to be there, even though it doesn't have pointers to its position in the list. So this one would return -1. We need to make it return -1 by removing it from, removing that node from the list. The way we do that is by getting the key that was removed and deleting that from the hash map. So it's going to be this.map removed.key. So we need to return, I guess, the node that was removed from remove front. So we could just return front, or we could have remove return the node as well. I don't actually know if we need it like this. We'll just keep it like that for now. And other thing we're forgetting is when we get an item, we need to make it used again. We need to refresh in the list. So we need to call this.list.remove node and this.list.append node. So we're removing from the list and we're adding it back to the end of the line. Okay. Okay, something about this logic is wrong. Let's look at this. So if node exists, we need to remove it, then add it back into its spot. Otherwise, if node doesn't exist on the map already, we need to add it into its spot. So this.list.append new node key value. We really don't want to add, so if node already does this, we don't want to add the node back in because the value is changing. So here, this should really be a node with a new value. We don't have any update method, we're just creating a new node. It might be less memory efficient because it'll be a different memory location, which could affect cache locality. We won't worry about that for now. So this.append new node key value. And I don't know how or when I wrote this, but in all of these, at least in here, in both of these, we need to update the value of the map. So like we would need to say, you know, this dot map key is equal to whatever this node was, you know. And we need to do that down here. If the node didn't exist before, you know, we need to create the new node, add to the list, and add to the map. Looks like, yeah, we kind of wrote that logic down there, but we really can just take all of this, use it in both the cases, whether it existed before or not. think that's all we need. So if the node exists before, remove it. Otherwise, if the node didn't exist before, but we're at capacity, we need to remove, the front node from the list. And then once that's all handled, we create a new node, we add it to the list, we add it to the map. So we have remove method, remove front method, pen method. Aha. So notice how I called we don't really need any methods on the DL node class. We could kind of take this logic here and wrap it in a .remove method on the DL node class, but since we're already exposing the prev and next properties anyway, I don't think it matters. Oh, that's old video. Okay. Whoopsie daisies. So I think this might work. So I guess we'll explain why this precondition is always satisfied, and the reason why node is never going to be head or tail, why we don't have to yet check if node equals head or tail, is because the only time we're passing a node into remove or append, I guess that precondition applies for both append and node, is from the nodes returned from our map, and only time we're putting nodes into the map is actual value nodes, actual nodes that have keys and values. It's never going to be one of the head or tail nodes. Alright, let's see how many errors we have. Okay, line 33, cannot read property 1 of undefined. Okay, so we need a constructor. So yeah, we need to find the map that we've been using. We need to create the list that we've been using. And that might be all we need. Okay, node is not defined, right? I think the class we made was called DL node. So we only need that input. No, we need on get as well, right? Yeah, so I think this right here is actually an issue. We need... Nope. The value's never going to change. Again, it's just the position of the list, of the node in the list that changes. So the node's the same, just position changes. Okay, so test case got accepted. Let's hit submit. There we go, it worked. I don't think... I've run this before and it's been 90% faster, not 99% faster. I think it's just luck of the draw. Sometimes when you run it on Leetcode, yeah, now it's running slower. So I think we're at the fastest you can get, pretty much, algorithmically. You might be able to do some like memory locality things by not creating a new node each time. You might be able to like fetch the old memory location and just update the value there. And maybe as you get larger and larger data sets, that'll give you better and better relative performance.